Hello, this is question 4 from the 2018 Maths. Consider two circles, S1, S2, centered at A and B. Okay, fine, we've got big one and little one. Radii root 6, which is marked on there, and root 3 minus 1, which is marked on there. Suppose that the two circles intersect at C and D. Fine. Suppose further that the two centers are a distance 2 apart, also marked on there. Sketch is not to scale. Find the angle CBA. Deduce A and B lie on the same side of CD. Right, well, that should be fine. Let's zoom in at what we've got then. CAB. So that's going there, that's going there, that's going there. They told us 2 apart. That's the angle that we want. B to C is the radius of the small circle, root 3 minus 1. C to A is the radius of the big circle, root 6. So this is classic cosine rule then, isn't it? So we're going to have root 6 squared, so 6. 2 squared is 4 plus this thing squared, so that would be 4 minus 2 root 3. Then we need to take off 2 times, so 4, 2 times 2 times root 3 minus 1 times cos theta. We got loads of 2's we can get rid of here, haven't we? Let's deal with the 6 and the 8 first. So let's get rid of that, that, and that, and make a minus 2. So you then get rid of all these minus signs. Then get rid of all these 2's. So we've got 1 is equal to root 3 plus 2 root 3 minus 1 cos theta. So cos theta is going to be equal to 1 minus root 3 over 2. Let's put it as minus 2, 1 minus root 3. So that's minus a half. So we're going to be, what for cos, that'll be 120 degrees. So theta is 120 degrees. So if that is 120 degrees, then, well, it's going to have to lie to the left of, yeah, it's got to be, isn't it? So, yeah, it fits with this thing of A and B lie on the same side of CD. So how are we going to describe this? So if theta is greater than 90 degrees, then A and B on same side of CD. Right. Part 2. I've filled up a lot of screen already. Show that CD has length 3 minus root 3. Hence calculate the angle of that thing. Right, okay. So how are we going to get to this? So maybe we want to go off of, what do we know on all of this? We've got, just trying to think. Well, I'm going to do another sketch. I've got, let's get a new sheet up, draw this again. So we want now, let's look at the B, D and C. So B, C, D. So we know that this angle here was 120. So that is also 120 all the way round. Symmetry means that that's going to be 30. So we should be able to deal with this quite happily then. So we know that length. So a half of CD is going to be our radius here, root 3 minus 1, times sine of 60 degrees. So CD is going to, well, sine of 60 degrees is root 3 over 2. So we're going to have root 3 minus 1 times root 3, which is 3 minus root 3. Okay, that's what we wanted. And then we want angle CAD. It looks like it's going to be cosine rule again, doesn't it? Because now we've got the length. Yeah, we've got 3 lengths. So yeah, it's going to be cosine rule again, which means our side opposite the angle is this thing we just worked out. So we've got 3 minus root 3 squared is going to be, well, 6 plus 6 minus 12 cos, or whatever, let's call it phi this time. So, right, we've got then 9 plus, so that is 12. All right, the 12s are going to cancel. on these things. And we've got, anyway, 6 root 3 is equal to 12 minus 12 cos phi. Cancel those, get rid of the minus signs. So cos phi is root 3 over 2. So phi is going to be 30 degrees. So that is our CAD, right, which is a bit sharper than it shows on the picture. Show that the area of the region lying inside the circle S2 and outside the circle S1, so the shaded region, is equal to all of that. Right, always like these sort of ones. They do these questions a lot on the physics papers, or the math section of the physics papers. So that area then, let's do our little word equation. So that area is going to be the sector of B minus the sector of A plus, what are we going to have to put back on? We have to put back on, yeah, we got that, minus the sector of A. So we're going to have to then put back on a couple of triangles, aren't we, after all of that, because the sector of B is giving us this bit, but we're taking off too much. We're taking off those two triangles. So let's just illustrate what I'm saying. So that's our sector of B. So that's the bit we're starting with. But then the sector of A that we're taking off, okay, it's taking off that bit which we want to take off, but it's also taking off all of this, that dart. So we want to add on two triangles, two ABC triangles is what we're wanting to put back on. So the area of sector B, so it's 120 degrees there, so we're getting a third of pi r squared, and that's our root 3 minus 1 all squared. Then we want to take off, and it's 30 degrees we've got there, so that's a 12th of pi r squared, which is 6 pi in that case. And then we want to add on 2 lots of a half AB sine C. We might want to do on this. We want to do it that way. The 2 lots of this, or do we want to do it as a, no, because we're going to end up getting a sine 15 in there. But we can do a half base times height. Half the base is 2. So 2 times a half times 2, and the height is half of CD. So a half of 3 minus root 3. Right, so what's this leaving on all of this then? We're getting, just seeing if there's a sort of quick way of doing anything with this. I don't think there is there? So we're going to have 4 minus 2 root 3 over 3 times pi, minus pi over 2. And then we're, well, that cancels with that cancels with that. So we're just doing a 3 minus root 3 at the end. How close is this? Well, it looks like I've just put that as one fraction at the start then. So let's put all this over 6. So pi over 6. So we're doubling this one. So we're going to have an 8 minus a 3. So that's our 5. And then we're doubling it to get 4 root 3 plus 3 minus root 3. Right, fair enough. Last part then. I think we need a new sheet on all of this. Last part. Suppose that a line through C is drawn such that total area covered by S1 and S2, okay, so the whole of the eyeball shaped thing, is split into 2 equal areas. Let E be the intersection of this line with S1, and X denote the angle CAE. Right, so this thing here. Right, so we're moving E around the circumference of S1 until we're splitting the area in half. Okay, this is where another one of these ones where it's useful to look at these pictures like they're actually moving. You know, E is a mobile point. This is not just a fixed diagram. Right, where was I on all this? You may assume that E lies on the larger arc CD of S1. Right, so we're moving E from D round to C, or from C round to D, whatever way you want to look at it. But they seem to have sort of, I don't know, it looks to me as though it's moving clockwise from D round to C, but it's all the same, whichever way you look at it. Write down an equation which X satisfies. Explain why there is a unique solution, X. So we have worked out the area of the whole eyeball. So we know that the total area is equal to the area of the big circle, so pi r squared, so that's 6 pi, plus that area that we worked out in the last part of the question. So we've got 6 pi plus pi over 6, 5 minus 4 root 3, plus 3 minus root 3. So we've got that as a total area. Now we have to do a new bit of geometry then to try and see what we've actually got on the areas created by E. So we've got an annoying shaped bit on the right. So I'm thinking we go for the shaped bit on the left. So that means that the half area that we're getting is this sector of S1 plus this triangle. So we've got the sector S1, so that is the total area, our 6 pi of the big circle. And then the angle round here is a 2 pi minus x. 2 pi minus x, and then divide that by 2 pi. Right, that's that bit. But then we need to add on this triangle. We've got the CAE triangle that we need to add on. And on that one, well, we can do a half AB sine C on that one, can't we? So we can do a half. Both of those are root 6. So we'll be doing root 6, and then sine x. Because they've just said, write down an equation which x satisfies, so that we haven't actually got to solve this from the way they've worded it. And we can say these things are the same then, can't we? So we can get rid of that and that, make that a 3. That's going to be a 6, make that a 3. So we're saying that 6 pi minus 3x plus 3 sine x, so that's what we got from that half area, has got to be half of the thing at the top. So 3 pi plus pi over 12, 5 minus 4 root 3, plus 3 minus root 3 over 2. So we've got all of that. I mean, I suppose we could trim that down a little bit, like we could get rid of that and make that a 3, but whatever. We've got an equation that x satisfies. And we have to explain why there's a unique solution for x here. So what's happening then? As we're moving from D around to C, yeah, I mean, that area is just getting smaller. So yeah, that's quite an easy explanation on this one then. So as E moves from D to C, so i.e. x goes from, what did it start at? It was 30 degrees, wasn't it, originally, I think? X moves from 30, so pi over 6 to, what would it be? If it goes all the way around, it'd be at 2 pi. The area, well, it's the left-hand area. So the area decreases. So let's say the left-hand area, so in equation 1, so equation 1 continually decreases. Therefore, there's only one position, one x value for each area. Right, there we go. Yeah, that was quite a nice question. Lots of, I mean, it was, the only thing I didn't like about it is I used cosine rule twice, and I'm not a big fan of using cosine rule, but they came out fairly easily. That was the thing. When they're just giving you all of those sides and asking you to work out an angle, then it does seem to be the way to go, really. So, you know, sometimes it does have uses, but, you know, what can you do? It was fairly straightforward, I suppose. Just draw out the little bits one at a time as you're going through, pick out the bit of the diagram that you're actually concerned with, the triangles that are of interest, mark on the sides, work out the angles, and just repeat. So it took up a lot of space. I don't normally have to have 3 sheets to go through a question, but that's the value of actually drawing these things out. But another nice geometry question. I always like question 4, and this one's not really any different.